Hello, and today we're going to do the second installment of waves. This is Unit 10. We're going to talk about equations of waves as well as developing waves and how the waves travel through the ocean, and end up when we get to tsunamis, which will be our third part. So a couple equations we have to talk about in terms of waves. One is wave speed, wavelength, the length of the wave between a crest and a crest, or a trough and a trough, and period, how many of those would pass a certain point at a certain section. Like you were standing at the end of a pier, you could count the waves going through and figure out the speed. So the speed is determined by a distance and a time. Usually we're talking about feet or meters, and seconds or minutes. Then we have the frequency. The frequency is how many waves actually hit a certain point at a certain time. So we take that period again, and we take 1 and divide it by the period. So if you actually had a period of 7 waves per minute, it would be 1/7. That would basically mean you're getting 1/7 of them hitting every 7th of a minute. So we get 7 of those per minute. Wave speed of celerity is usually given in meters per second. Universal unit of both time and distance. And then what we do is we take the period again, number of waves per second, and actually multiply it by 1.56. So if you had a wave that was traveling at 20 seconds between waves, and you multiply by that, you can get it. And a typical ocean wave has an 8-second distance, 8-second period. These are called trade wind waves, and at that distance they're actually moving at 12.4 meters per second, or 28 miles per hour, a little faster than what you drive through a neighborhood. Next thing we're talking about is ocean waves, and we actually have lots of different types of waves. This is the sea surface, so if you've got a wave that's less than a centimeter tall, we call those capillary waves, very light winds. And basically what that means is when the wind actually dissipates, wind stops, these capillary waves stop, and the ocean becomes flat. A little larger than that, we go to what's called chop and swell. These are the normal waves you get out in open ocean. It usually takes a stronger wind. These are what are called gravity waves, and what's going to happen once the wind stops, these will travel until gravity starts yanking down on the crest and flattens it back out. Seiches are not quite as tall. They're going to slosh back and forth in an enclosed area. Tsunamis, a little taller, but again, this is an open ocean. That's about 1 meter tall. So actually that's about 10 meters tall. So it's not a very tall wave in the ocean, but once it gets to land, it actually starts standing up and can become tall. And tides can be very tall, and we actually have what are called diurnal tides and semi-diurnal tides, one happening every 12 hours, and you can see that's getting up at about 1,500 centimeters, so about 1.5 meters, and then we can get up a little higher than that up there when we talk about 10,000 centimeters. Sea waves, we actually, if you take a look at this diagram, we have knots of wind, and knots a little bigger than a statute miles. We have time, and we have size of waves, and we have length of the fetch. If the wind blows for 25, I've got to imagine that's probably knots also, or 50 or 100 or 250 or 500 or 1,000 or 2,000. You can see these waves get taller, and they also get farther apart. So there are 3 things that actually help put energy into a wave. First one is wind speed, which is usually in nautical miles. It's a direct effect, which means as the wind gets faster, the waves get bigger. Fetch, this means how far does the wind actually blow across the ocean. And again, the farther the wind blows, the greater the wave energy and the greater the wave. And the last one's called duration. Duration is how long does the storm last. If we have a storm lasting 2 minutes, probably not going to create big storms. Happens to last for 2 weeks, it's probably going to make some pretty hellacious waves. You can also get a very chaotic mixture of waves if you've got multiple storms, multiple fetches, storms being different sizes, and you have storms with different wind speeds, all being pushed out in 360 degrees away from the storm, running into other storm waves. You can have a very chaotic mixture of wavelengths and wave heights, and that's what happens in the open ocean. Savage Sea Wave is a thing that I'm going to have my kids do tomorrow. It opens up. It's also quite loud, and it does have ads. It is a PBC home, and it's going to actually look at the 3 waves, I'm going to ask my kids to look at the power of waves first, then look at freak waves, tsunamis, and winds of trade. There are other animations. This is the actual site we're on for the wave machine. You can actually see deep sea simulators. You can see Trias, which is the 1960 gasoline-filled sea sub that actually went down to the bottom of the Mariana Trench, deepest point in the ocean. And you can see how we can actually look at satellites. There's some videos in here too that will look, and I'm going to have my kids look at the power of waves first, and then these three, and then they're going to click start. Actually, they're going to read what they're going to try to do, and this simulation actually tries to show you the three factors: wind speed, fetch, and duration, which helps determine the height of a wave. And they're going to click start. They're going to actually learn about wind speed, and you can see wind speed, and it talks about nautical miles or miles per hour, and they're going to pick different speeds. It'll go to fetch, and fetch is talking about the area of open water that it goes through, and you actually pick these out at nautical miles. I'm just going to pick 10, and then the other was duration, and they're going to pick one of these, and when they do that, it'll actually go to a ship and show you that I've got 2.6 feet tall waves. And if you want to see that again, there it goes. Doesn't do much to the ship, and it actually gives you the three things you picked. So that's the first thing they'll look at. Second thing they're going to do is they're going to actually look at wave dispersion. And wave dispersion is talking about waves and how fast they travel. Longer wavelengths travel much farther than shorter wavelength waves. So if you've got waves that are 50 feet apart, they're going to travel farther than waves that are 5 feet apart. And that's just the way the energy, how long the energy lasts to create the waves. Waves travel in groups, or what are called wave trains, and wave trains usually have very similar characteristics in terms of wavelength and wave height. And swells out in the ocean, same sort of thing. If you go out in the ocean, and I'll show you a couple pictures of swells, they make up waves that are very similar in terms of wavelength and period. Wave trains work by, you get a low pressure. This one's actually over the United States, but they happen in open ocean too. If you watch that Earth Null School from part 1, or if you go to earthnull.school, you Google that, you can actually find the site. But the low pressure in the northern hemisphere spins in a counterclockwise direction. This is the low. The low would be actually right there in the middle of this comma-shaped cloud mass. If that sits over the ocean, what it's going to do is it's going to start throwing wind out in all directions, and it'll actually start creating waves. And the first wave goes out, the second wave comes out, and the third wave comes out, and the fourth wave comes out, and these just travel out away from the storm. And what happens eventually, gravity will, because this is the oldest wave, wave number 1 will get pulled flat, and now wave number 2 is in the lead, but it picks up a wave number 5. Number 2 dies out a while longer, and we get a 6, and 3 dies out and we get a 7. And these trains actually still, you see 4 waves there, and you have 4 waves there, and you have 4 waves there, or 4,000 waves, 4,000 waves, 4,000 waves, and they just keep going apart. You can see the storm, which was right there. It travels away from the storm, travels away from the storm, flat ocean, this train just keeps moving out, and it's going to move out in all 360 degrees. So if they form there, the trains will all go out this direction, and it's sort of like throwing a rock in the water, and you watch the water where the rock lands flatten out, and you see the waves actually traveling across the ocean. Those are wave trains. Okay, here are swells. This is a nice blue day. Winds out there, and you can see these waves all look very characteristically the same. Wave height and wave distance. And then we have the same thing. These are swells caused by stronger winds in a storm, so strong that the wind's able to grab onto the crest, the top part, and actually blow it over, giving the water molecules. They're still doing these little orbitals, but the water that you see is white. It's actually blown over because of the high energy and the steepness of the wave. We have wave interference. Waves actually interact with each other. We have what's called constructive, and this actually makes waves higher than and lower, higher crests and lower troughs. The wave height is actually higher. It is additive, so if you've got a 2-foot wave running into a 6-foot wave, when that 2-foot crest hits that 6-foot crest, you're going to have an 8-foot crest. If that's a 4 foot, 2 feet up, 2 feet down, 6 feet up, 6 feet down, 12 foot, running into a 4 foot, you're still going to actually get one that still is, very tall, much taller, and much lower, so the wave height is going to increase. You have destructive, so if the one crest actually runs into another's trough, the crest will actually fall into the trough, and it could, if you had a 2 foot wave, the 2 foot crest, the 2 foot trough of the other wave will cancel each other out. And then normally in an open ocean where you've got the storms coming from all directions, you get what's called a mixed interference, and you get the wave trains of different heights actually causing all kinds of problems. Here's a picture of two waves, one green, one blue, and you can see the crests align and the troughs align, but you can see the blue wave is traveling a little faster, and what it does in the B version is it takes that height of that green one and that same height of the blue one and adds them together to make a much taller crest and then a much lower trough. And then you can see as these get offset, the crest gets a little the crest gets a little shorter, trough gets a little higher, and then eventually when they're out of sync where one crest hits in the trough, you get a relatively flat ocean, and then as the blue one keeps picking up, you can see you get a different one. So you get constructive interference where you add the two together, you get destructive where you subtract the two, one from the other, and then you get constructive. Here's another view of actually taking a look at this is the constructive interference. So if you take this wave and you put it in phase with this wave, you get a wave that's a lot larger. If you get this wave out of phase with this wave set, you get a flat ocean. And normally what happens is you get mixed oceans where you get large wavelength tall versus shorter wavelength tall or small, and it actually gives a much larger variation of waves in the outcome. Here is a YouTube video which you could watch if you want to. We're gonna watch a little of it, and what it's gonna do is talk about actually this one we're probably not going to show because it's 7 minutes long, but it talks about double slit light experiment, and it will eventually show about constructive and destructive interference, but again we're not going to watch that because that's too long. Video is going to get long enough already. I will put all the YouTube videos in the comment below the video so you can click those and see them. Then we get what are called rogue waves. If you get constructive interference of lots of different storms where you can get, let's say, 10-foot waves for the most part, and then all of a sudden the 10-foot wave runs into another 10-foot wave, and you get a 20-foot wave, and that one runs into another 20-foot wave, and you get 40-foot waves. And basically what you get is you get a still water line, and you get a much larger crest. And what it would look like, and this is when storms meet, what it would look like in an open ocean is something like this. That's a rogue wave, where you normally get waves that are breaking right over the bow of this ship, and now you get this one that's actually 20 or 30 feet. And I'm not sure how big this tanker is. This is not one of the very large tankers, but that's probably 30 or 40 feet taller than, and probably as tall as the what the heck's the console call where the captain sits. It's probably taller than that conning tower if it was an aircraft carrier. Probably not called the same thing on a tanker, but probably taller than where the tallest part of the ship. You do have what are called shoaling waves. These are when they actually hit the surf, or what's called the swash zone. If you've ever been to a beach, this is where the waves are breaking. Basically what happens is the wave speed decreases, so the first wave hits it and slows down, the second wave comes in and catches up to, or at least starts as to, so the length decreases, and as you actually slow down the wave, the water piles up and you get a much taller wave. When the steepness gets to be 1/7, the wave breaks. Surface tension is no longer able to hold the water. It's not a nice smooth surface, and the water actually starts falling. Here's a picture of a swash or a surf zone, and you can see out here capillary action or surface tension is causing the water to have a nice smooth surface. As the water gets shallower, and there may be sandbars and things out here, but if you take a look at these wave sets, they get closer and closer as they get to the beach because they've slowed down. The waves do get taller, and they eventually get to the point where they break. Give you some scale, these are people, so this is a pretty good size picture of an ocean, but this is the swash or the surf zone where the waves are actually going to start breaking. We have these breakers or these surf zones coming in 3 different slopes. If you have a very gently sloping beach, you get what are called spilling breakers. If you have a steeper beach that comes up and they stand up faster, you get what's called a plunging breaker. And then if you actually get a very steep one, it's almost like you have a wall there, you have what's called a surging breaker. And these are 3 breakers. Normally what you get is a spilling breaker or a plunging breaker in most beaches. This one you'd actually have to have like that video that I showed in class from Earth Revealed, where you have a wall or a cliff to actually make these surging breakers. We have wave refraction. Wave refraction, the waves actually change angle. As they actually get closer to the beach, they slow down and they straighten out. They're not going to come perfectly straight, but you can see they actually get closer together because they're getting tripped down by right there. They become from deep water waves into shallow water waves, so they start standing up, they start slowing down, and they start to break. We also have wave refraction and diffraction when we have coastlines, irregular coastlines, where the water actually is deep along this cliff. It travels more in a straight line. Where it actually hits closer to a shallower zone, they sort of spread out, and you get erosion happening at what are called the headlands. And you get deposition, sand actually being deposited for beaches in what's called the bay. And that's again all caused by wave refraction. You have diffraction also, where the wave actually comes in and where it hits something that sticks out, and this could be rock or a man-made jetty. What happens is it bends out. So any kind of barrier to wave actually transfers the energy around and back in, and you can see it actually diffracts, it changes direction. A real good example is this picture. I have no idea where it is. It is on the west coast of the United States. There is a headland and there are bays, so you get erosion, and you can almost imagine these rocks as being out here and they've been worn away, but now we actually have the waves coming in this direction, and they're hitting all kinds of impediments which are bending the waves, making these concave or convex depending on which side you're looking at. You can see the waves sort of straighten out, and then they get in between these two, and you can see they're bent around there. You can see they're actually moved into this area, they actually move into this area. If it cuts through here, you can actually get a cave or a tunnel if it goes all the way through, and eventually it'll end up washing away all these rocks, putting them on sand on these beaches, and then you throw in jetties and all that stuff for dams, and you make all kinds of problems with that. So how did this form? Waves coming in the open ocean, minding their own business. They hit this island, and then they hit this island, and they bend in, and the water becomes deeper, and it drops sand. And what it did is it actually made a sandbar that during low tide you can walk out to this sea stack. During high tide, this is all in water, and that's what they would call these things. I guess this stack out here is probably big enough to call an island, but you can see lots of islands and sea stacks, lots of places that used to be touching the continent, but it is kind of cool. Wave reflection, this is when it actually bounces off a steep slope or a seawall like this, and here comes an ocean wave, and if you watch this crest, it hits the wave or hits the wall and then bounces out and then runs into this next crest, and that bounces out and moves into the next crest and the next crest and the next crest, and then we get what are really called standing waves, where if I could move my mouse to a place like right there, you can see there's really no motion. So we do go nodes and antinodes, which we'll get in sessions and internal waves. Reflection of this usually causes constructive interference, and it causes crests to be larger than they normally are. Standing waves, which we just talked about, these are two waves of the same wavelength moving in opposite directions. You have a node developing where you get no vertical movement, you get lots of horizontal movement. And you have an internode where you have no vertical movement, or you have the greatest vertical movement and very little horizontal movement. And here's a YouTube video. This is 5 minutes, but I'll show you parts of it. And this is actually Lake Superior and the sesh that happens in Lake Superior. I'm sorry, this is a river in Hawaii, and I will put these links in here. This is a totally cool place to surf because you can surf standing still. And what they basically did is they dug a sand trough through a beach between a river, and actually I think I'm going to let this set up for a second. They actually let this thing form, and what's happening is the water from a lake is actually now moving into an ocean. Normally this part of the ocean, it's in a cove and it doesn't have very good waves, but what you get what is called a standing wave, and the wave sort of stands still. And let me play it now. And what you can do, and it's not working very well. What's it doing now? Yeah, you should watch this on your own. I'm taxing my laptop here, and there was a little bit, but you can see the water's actually moving in this direction, and it runs over and it piles up and it gets to 1/7, and what you're doing is you stay surfing in one little area, and that's enough. It's actually quite a cool place to go, and I'm gonna definitely have to get to Hawaii and see that. Okay, here is the node and antinode, and notice that the node, and this is time in minutes, so if you actually go to a quarter minute, 15 seconds, it flattens out, and then you get a motionless area where it kind of hangs up, and then it sloshes back down to flatten out. And if you take a look at these dots, they're moving back and forth, and you get the area on a flat ocean, which is this blue-black line. You get the node that stands in place where you basically have no motion, and then you get the antinode where you've got an up and down motion but very little horizontal motion. Here is the Lake Superior sesh, and let's see if this one plays. What it's going to do is it's going to show you a beach and a dock, and it says the sesh is out. And basically what's happened, it's sort of like a tide has gone out, the sesh has gone out because it's building an antinode someplace out in Lake Superior, and this one doesn't look like it's going to go any better. What are we doing for? I want to keep it at 480. I don't want to go any lower than that. But if I move this over a ways, what'll happen, you can see there's a freshwater lobster, crawdad. And if I go to this point, what happens is here comes the water back in, and it eventually gets to a point where it deepens up, and it gets deeper and deeper, and eventually that antinode comes all the way back to shore, and you have what looks like a normal lake. So you can take your boat out, and that water will go back out, and it all happens in a period of like 15 or 20 minutes, and they're usually storm controlled. And I probably should have closed these so they don't come over the top of what I'm trying to do. Okay, and that is seismic, or that's the seismic sea wave or tsunami where we're going to stop. So we are done, and 23 minutes. Ugh.